In the previous lecture, we talked about vapor pressure and we talked about boiling point. So I want now to use a special equation where we can relate vapor pressure and boiling point. This is the Clausius-Clapeyron equation. So this equation unites or lets us interrelate vapor pressure, the molar heat of vaporization for a given substance, and temperature, where the temperature is referring to the boiling point. So we have a couple of variables in the equation, the PVAP, which is the vapor pressure. Um, we have the molar heat of vaporization, okay, and we have the gas constant R. Now, you want to use this with thermodynamic units. So the R that you want to use whenever you use this equation is 8.314 joules per mole Kelvin. And for that reason, you want to always make sure that you convert your molar heat of vaporization into joules per mole. Okay, that should be, you want to keep those units consistent so that they'll cancel. So the natural log of the vapor pressure is equal to the negative delta H vap over R times 1 over T plus a constant. Okay, now who knows what this constant is? Nobody knows what it is, so I'll talk about that in just a second. The temperature, in this case it's reciprocal temperature, you want to make sure that your T is always going to be in Kelvin because you need it to cancel out with the units of R. Okay, so the temperature must always be in Kelvin. Now, this is not the useful form of the equation because we have this constant here that we need to get rid of. So the reason it's written in this form is simply to get it in the form of y equals mx plus b, where the constant is the y-intercept, the x is the reciprocal temperature, the delta H vap over R is the slope, the minus delta H vap over R is the slope, and the natural log of the vapor pressure is the y. So we write it in the form of y equals mx plus b because that enables you to take two sets of conditions, y1 and y2, and x1 and x2, and subtract one from the other to get rid of that constant. So here is the useful form of the Clausius-Clapeyron equation that you will be able to plug numbers into. We're combining two sets of conditions, okay, two sets of temperatures, two vapor pressures to get this form of the equation. So the natural log of the vapor pressure at temperature 1 over the vapor pressure at temperature 2 is equal to now positive delta H vap over R times 1 over T2 minus 1 over T1. Be sure you don't scramble the labels here because the sign being positive of that slope depends on having the T1 in the numerator here and the T2 in the denominator here, and also the order of T2 and T1 on the other side. If you stick with this useful form of the Clausius-Clapeyron equation, you can solve any problem involving vapor pressure and boiling points for liquid vapor transitions. Let me give you an example of a problem that you can solve using this version of the Clausius-Clapeyron equation. So the molar heat of vaporization of water, something I gave you in a previous lecture, is 43.8 kilojoules per mole. We know, of course, that the boiling point of water is 100 degrees Celsius at atmospheric pressure, which is 760 torr. What is the boiling point of water at 25 torr? So we just need to kind of assign our variables to solve a problem like this. You need to keep them together. So if I'm calling T1, I'm just going to say T1 is 100 degrees Celsius. That means that the PVAP at T1, is going to be the 760 torr. Now, remember, you must convert the temperatures into Kelvin. So I have to add 273 to convert that into Kelvin. The T2 is what I want to figure out. The boiling point of water at the vapor pressure at that T2, I know is much lower. It's 25 torr. So basically what this question is asking is, can you figure out what the boiling point of water is going to be at this super, super low pressure of 25 torr? So we need to take these variables and plug them in to this version of the Clausius-Clapeyron equation. Okay, very useful version of the Clausius-Clapeyron equation. Let's do it. All right, I'm going to move down here so we have room to do the problem. The natural log of the vapor pressure at T1 over the vapor pressure at T2. So that's going to be the natural log of 760 torr over 25 torr. Now I want to point something out to you here. As long as the units are the same, since this is a ratio, it doesn't matter what units you have them in. So you could convert them into atmospheres, right? And it's the same because it's a ratio. The units are going to cancel. So just make sure that the units are the same for the vapor pressures. This is going to be equal to, now we have, looking at the Clausius-Clapeyron equation, I want to put delta H vap over R. Now, delta H vap, I must convert it into joules. So that's going to be 43,800 joules per mole. And my R, of course, is 8.314 joules per mole Kelvin. And that is going to be multiplied by 1 over T2. T2 is the thing I don't know, my unknown variable, minus 1 over T1. So that's 1 divided by 373 Kelvin. So now you need to simplify and do the algebra. And this is, just make sure that you use, please excuse my dear Aunt Sally. What I would do is take this quotient, take the natural log of that quotient, divide it by this quotient, and then isolate your terms, okay? Everybody has their own way of doing it. I suggest that you pause this video and make sure you can do the algebra and solve for T2. T2 should come out to be about 301 Kelvin. All right, make sure you can get that answer. If I subtract 273 from that, that's about 28 degrees Celsius. So you need to practice using this Clausius-Clapeyron equation until you make sure that you can do the algebra without making any mistakes. And you should also make sure that you can pull any variable out of this equation. This is a particularly difficult example, but you should also be able to calculate either of the vapor pressures. You should be able to calculate molar heat of vaporization. All right, so in the homework, you'll get practice using this equation backwards and forwards. This illustrates how if you reduce the vapor pressure, you also get a massive reduction in boiling point. Okay, so we know this, reducing the pressure reduces the boiling point. So please practice the Clausius-Clapeyron equation, and I hope this one makes sense.